Okay. Welcome to day 5. Thank you for those of you who have made it, through the entire week. So as shown in the agenda, the plan for today is we call it kind of a hackathon. So we're going to focus on developing models for a specific data set. And in particular, we thought it appropriate to talk about or to have you all work on multimodal classification in particular, because it's the ability to analyze different types of data, different modalities, different observatories, what have you, is super critical, and also at least partially the topic of the workshop. And so AJ is going to introduce what we've been doing within Apple Cider, which you've seen aspects of during the week. So we hope it's prepared you reasonably well to hack away at, let's say. And so AJ will talk a little bit, and then Felipe will introduce the notebook that we have planned. Otherwise, I think you can take it away, AJ.
Okay. Hi everyone, I'm AJ and I'll be talking about apple cider. So a little bit of background, as I'm sure we all know, there are lots of updates or alerts that come from ZTF. Okay. And Ruben expects a significant amount more. So having some robust classifying system that works within one of these production pipelines that can accurately go through a lot of data and help us decide what to do follow-up on is really important. So apple cider, the letters are all in the name. So it's applying multimodal learning to classify transient detections early. Our motivation, so there's kind of two parts. So there's the ZTF production aspect, which is kind of, you want some real-time classifier, but there's also this concept of foundation models, and foundation models are LLMs or large language models, stuff like ChatGPT or Llama that are trained on huge data sets, and then can be used for other downstream tasks. So kind of moving towards something for that. For time domain astronomy, there's a couple other classifier that are moving towards a foundation model in time domain astronomy. There's Maven and there's Astrom 3, but they do a little bit of different things than Apple Cider does. We're using 4 modalities, so photometry, metadata, images, and spectra. And then we're also classifying full supernova and other types of transients and variable sources. And just a proof of concept thing. So there's already a lot of ML models in production at different telescopes, and ZTF in particular uses BTS-bot, which this took some inspiration from. So again, there's kind of the two versions we have. So the ZTF version, which would be for production and using to inform what objects we would go do follow-up spectra on. So that's why spectra is not included, it's just photometry, images, metadata. And then kind of the all version is moving towards that foundation model style thing, where we're taking in more data and data that we get after the fact, after you followed up, which is of course spectra. Yeah, so this is just another schematic. So how things work, if you don't know too much about like ZTF production. So you get alerts from ZTF, but those actually have to come from alert brokers like Kowalski and Boom. And then Apple Cider would take in those alerts, classify them, send that information to Sky Portal, and that is what would facilitate follow-up spectra. And then once that follow-up spectra is taken, we'd use that again to train Apple Cider on the spectra. So just some brief stuff about pre-processing that we'll go over quickly. So as one might imagine, we can't do follow-up on every object. So there's an imbalance of what objects we actually have spectra on. And then also the other thing with Apple Cider is that we're only training on 10 days or less of data. So it really is kind of early time data where for all the modalities, we're not using the light curves, or although for photometry, we take in more data and can go up to I think 50 days. I won't go too much into detail on the photometry processing, but we have magnitude, convert it to flux, and then cut off at our desired date. Images, so they're cut down a little bit, and for images, you have a science image, a reference image, and a difference image. And a science image is the change that you saw and functionally why that alert was triggered. The reference image is some old archival image of where the object is. And then the difference, of course, is the difference between those two. So alerts also have metadata. So metadata in this case is stuff like RA, declination, distance between nearest sources. So that can be really informative for classifying objects if there's another galaxy nearby or just another star nearby. And there's also some calculated features using those things. So age and then like peak magnitude and magnitude so far. And then also the spectra, it just interpolated, and what's a little bit different about our model is that we're using spectra from a different, like a variety of spectrographs. It's not just the one that ZTF had, which is SED machine. We're using stuff from SDS, and a variety of other spectrographs. Okay, so architecture, we talked a little bit about this, so I'll just breeze through this really quick. And so for the multimodal version, right now, what we're doing is we're just averaging the log-its from each modality. And you'll notice that for AstroMin, which is the image and metadata models, they're already fused together before we fuse them with photometry and spectra. But in the future, we're moving towards a more sophisticated fusion scheme. So instead of just averaging, there'll be some more informed decisions about how you're weighting each modality and the importance based on the classification, like the object classification. So here's some results. I'll just talk about the comparison because this is more important for today, I think. So with spectra and without spectra. So we do use spectra to classify objects. It's really important for object classification, for getting an accurate object classification. But of course, in the production case, which is like the ZTF labeled as a ZTF version, we don't have that spectra. So one of the things that we're working on for apple cider is improving the results without spectra, because practically we're using images, photometry, and metadata to make the decision over if it's important enough to take spectra of. And you'll notice there's a little bit of confusion between the type 1 supernova and the type 2 supernova. So that's something also that we're going to be working on going forward. But the version with spectra does do pretty well. And one of the more important classes that we're interested in, at least is able to classify a couple of them, which is tidal disruption events. They're pretty rare. I think there's only 75 in our entire apple cider data set. So being able to accurately classify early if the object is a TDE is really important to us, and really valuable for additional like follow-up and spectra. Okay, so just looking towards the future of what's going on in the world of apple cider. So we have our first paper on archive, which you can check out, and also our GitHub repo for it. But we're planning on releasing an updated version of the spectra, and then a photometry / fusion update, and then in the future also an anomaly detection of apple cider. So there's a lot of things going on in the future. Yeah, that's all about it for me. And I know Felipe is going to come up and show you guys how to use apple cider with a notebook using the Bright Transient survey objects.
All right. Thank you, AJ. That was really nice. And I really encourage you to check the paper because it's looking super good. AJ writes super well. You should check it.
Share it. I mean,
Yes, well, the link is literally
link.
here. Yeah,
And
might be worth just opening, and it came out 2 days ago. Congratulations for all of us. Thank you. Yes, feel free to check. Cool. So let's move to the next part, which is the notebook. Okay, cool. So our idea behind this was the following. Apple cider were just coming, and we were very excited because there is a lot of work still to be done. So we decided to basically hire all of you to work on it with us. So I really promise you that although some details are really glossed over here, you're probably going to be able to get as good as the results as we got for our paper. There's a lot of room to improvement, and you're probably going to find your way with your creativity to get something nice. So, well, this notebook here basically describes a node deployment of Apple Cider that we had with different encoders for each modality, but doing a certain experiment with the fusion architecture. So just to start, you all know why do we want to classify stuff early, and that is why all data limited in this hackathon is limited to 10 days. And we're basically trying to classify the transients in the dataset among those 5 broad classes here. So it's basically the same classes in the confusion matrix that AJ showed. We have supernova type 1, which is basically all of those here in the same class. We have supernova type 2, which is all of those, and then some confusing factors. So here we have cataclysmic variables, which should sometimes look like all of those transients for a very small amount of time, but only on photometry. You will surely be able to discern them well using images or metadata. We also have AGN that suffers from the same curse, and TDEs, which are like also a transient with a peak, but on a longer time scale that also can confuse your model. So this is our zoo, and hopefully by the end of the day, we'll be able to make a nice confusion matrix showing how we separate those classes using the model that you guys are going to build. Okay, so because this is a hackathon, right, we need some form of metric to keep us from just trying weird stuff. So our metric for today is going to be balanced accuracy. If you have trouble calculating it, just let me know. I didn't include the formula here, but we can code it together. It's basically your usual accuracy, but on a weighted average, in which the weights are the relative appearance of the classes there. So that is supposed to be fine. The way that the notebook is wrote is basically the following. So if you try to run the full notebook, you won't be able to do it. Just because I redacted some parts of the code and I included some exercises in the middle. And sometimes I just didn't include anything and just said, oh, do this, please. Also, again, I told you to be creative, right? So any like creative ideas that you have for either Fusion or for any of the encoders for the modalities are really welcome here. But because we worked this like full semester, we have some suggestions on how to improve this model. It's basically the path that we took. And all of those suggestions are going to be highlighted by the try this in a given markdown cell. Okay, so if you find this, and if you're feeling lost on how to improve your model, maybe try what's going on inside this cell first. That's a good suggestion. Okay, so just to set things up, you will certainly need all of those packets here, at least to run the stuff on the notebook. So you definitely need Torch, right? And Torch Vision, because we have a vision model in the middle of all of this. Torch audio might not be necessary for everybody. It really depends on your choice through the notebook. But again, the full kit, NumPy, Pandas, scikit-learn, Seaborn, all of that stuff should be in your computer. Cool. So in this cell, we basically do all the important importing. And we include some configurations that the model needs to run, right? So just some hyperparameters of the standard model that is coded in this notebook. So as you expect, deep learning, right? We have batch size, epochs, learning rate, all of that fun stuff that you can play around with. A lot of optimization can actually come from just changing those parameters here. So that is a good place to start exploring. Okay, so in this cell here, we basically define functions that you shouldn't mess up with. So the first one is the map that takes the actual spectroscopic classes to the broad classes in which you guys are going to classify stuff. So don't mess around with that. And here's just some normalization statistics that will be useful because we noticed that the metadata model was just intractable if you didn't normalize it, those norms. Cool. So your first task here is data exploration, right? You should know the data set with all of your heart in order to be able to build a good classifier, right? So as a first suggestion here, I'm asking you to calculate the relative proportion of the classes in the data set, just so you can notice if there is some imbalance or not. And if the imbalance exists, how bad it is, should you fight it, what techniques should you use? Of course, you should be able to, draw all the graphs that you want here, plot all the light curves, all the images, histograms with the metadata, distribution of some key features in the data set. So feel free to explore this. This is probably the most revealing part, honestly, on how to proceed forward. So, yeah. Cool. So just because data comes in an arbitrary packet, there is a guide here on how to open that data. So I already built a dataset class and a data loader here to ease your way out. But if you want, you can always play around with just changing how the data looks like in the first place, like reprocessing the data if you want. So you're also free to mess up with this. So. Okay, so here we start going inside the encoders, right? So because we're dealing with 4 different modalities, we need a machine learning model for each one of them, just like what AJ was saying. In this version of AppleCider, now we use like very fancy modalities with a lot of crazy techniques in the middle of them, and I tried to keep everything as simple as I could for this version here. So I would just gloss over each of the modalities, and if you have any questions, just please stop me. Okay, so the first one, which might be one of the most important, given that we only have 10 days, is photometry, right? So for photometry, I implemented a very simple transformer model here, the most standard transformer encoder that you can find there. The only cool trick is that instead of using all the transformer encodings to classify stuff, we're prepending a classification token. So it's basically a specific token at the beginning of your sentence, right? Because we're dealing with a transformer here that will accumulate all of information regarding class belonging. And we're going to use that to classify stuff. Feel free to change that as well, right? So the input for that model is composed of 4 different stuff. So it's basically a packet of the time in which a given observation happened, the G flux at that time, the R flux at that time, and the I flux at that time. As you can imagine, it's basically impossible to take a picture in all 3 filters at the same time. So what this model is really doing on the background is that when one of those observations is not available inside a given window, it just pads it to 0. So I think it's pretty standard stuff. This transformer is armed with a positional encoding, right? Just like what they use for standard transformers, feel free to play around with those as well. And of course, I don't expect anybody to be like super familiar and experts with transformers. So I'm planning this to be more like, very hands-on. I will be here to help you whenever you need. So if you have any questions about it, I have all the references in the universe to send you on how to implement those things. Cool. For spectra, we're using a very weird model that we were implementing before that does the following. So we know that CNNs are very good at discerning images, right? They're very successful at discerning images. So the reasoning here is, why don't we take our spectra, which is just a 1D kind of feature, and we turn it into an image? So basically, the person who implemented this basically took the spectra and created a grid with it, such that if you plot it, you're going to see that it looks like a nice 2D image in which one direction corresponds to the evolution of the spectra, and the other direction is just a repetition of the same wavelength, right? And then that is passed through a CNN, and that is used for classification. CNNs are like more familiar to people, but again, if you have questions, just please let me know. And for images and metadata, we use the single model, which is called AstroMin, which is implemented here, which is basically a fusion of a CNN for images, just CNN analyzing images, and a multi-layer perceptron analyzing the metadata. Just basically take both logits for those classes, slap them together. That is the output of that layer. That is more well described in the code. So now you have all the necessary implementations for all of those encoders that I just told you. Everything that is necessary to run that. And then we get to model fusion. So fusion is like maybe one of the most important topics in machine learning nowadays, especially because when you run your ChatGPT, you want to be able to upload an image and ask like, what's in my fridge so I can order it from Amazon or something like that. So here we're not fusing images with text like what models like ChatGPT do. we're fusing the information that comes from the encoders of photometry, images, metadata, and spectra. There are a bunch of ways in which you can do it. That is why it's such a big active area of research. The most simple thing that you could think about doing is that, well, I maybe pass all my data through those classifiers and I take the biggest probability, and that's it. That's my classification. So that is how people did it in the early days. Then you get the second step of that, which is, well, maybe just taking the biggest probability is not very good because maybe the models are not well calibrated. So why don't we take an average among all the probabilities? Or maybe an average among all the logits that generate those probabilities. And that would be what is implemented in AppleCider right now. In this notebook here, we actually go one step further and we ask ourselves, what happens if instead of a simple average, we take a weighted average of those probabilities? A nice question on that would be like, okay, but how do I choose my weights? Like, what is the relative importance of images, metadata, photometry? And we completely gloss over that, the answer to that question, and we pass it through a neural network. So the neural network at the very end of this architecture is going to decide which weights to pick for each modality. And it's going to be based on what is the confidence that the network has in the classification using each modality. So for example, if the network is very confident on the classification just by using the images, we bias the whole model towards that. So for example, if you have one of those triplets of images here, and you see that your source comes from the core of a galaxy, that's probably some form of nuclear transit, right? So we basically bias the weights of the model to try to classify TDEs or AGNs in our case. That's basically how it goes. Because that is just one form of model fusion, I also included a small table here with like a general guide on different strategies for fusion and stuff that you might want to try with this problem. So some people try what it's called early fusion, which is basically turning photometry, images, metadata, and spectra into bytes and just feeding that gigantic vector in a big model and trying to get a classification from that. Some people do intermediate fusion, which is what we're trying to do in this notebook, which is trying to make the information of the modalities mix together inside a neural network. And some people do what they call late fusion, which would be the example of like just using the biggest probability as your classification. So after everything was processed by the neural network, you choose your classification given a post-processing method. If you have questions about this, I love model fusion, so I could talk from hours about this. So I have nice suggestions for how to implement this. Cool. So here's a short description of what we are actually implementing. It's basically what it's called in the literature gated fusion, if you want to search more about it, but the code is already included. Cool. So this out here just separates the data. So it splits your validation and training sets, do some pre-processing, some class balancing if you like. And then we finally have the training loop. So this is the point in which you're going to choose your loss function and some optimizer and try to get the best weights as you can in the validation cell. And then finally, what's left open here is after you do all of your model testing and explore a lot of stuff, the final evaluation on the held out test set. So this cell here is empty right now because on the afternoon, after everybody experiments a little bit with the model, we will just evaluate everything and see the scores that we get to see like, yay, we did better than AppleCider 1, maybe. That would be amazing. That would be like AppleCider 1.5 or something. So yes, and this is basically the end of the notebook. Here, the last cell include a table with like some improvements that are maybe like worth exploring for this problem. And that's it. So I would like to know if you have any questions before we start.
And confirm, people were asking, you haven't pushed this quite yet, right?
Not yet.
Yes,
Yeah.
okay, yeah.
It's coming through after I finish. Yeah.
Understood.
Yes. Cool. Any questions? I can't see Zoom, so I don't know if there are questions there.
Yeah.
You can monitor that and just.
No checks on the Zoom. The Slack was asking about the notebooks. I think folks are ready to flow.
Yes, so I don't know, Michael, maybe you can maybe decide this. Would we prefer to work in groups or like individuals?
I think we should work as groups. I
Yes, me
think
too.
we need more, interaction's good. Yeah.
Okay, so feel free to make groups of what? How many people do we have? We have about 10 folks. Make groups of 3.
Yeah.
Yeah.
All right, so Felipe will push the notebook
Yes.
and especially, be active on Slack to,
Yes.
because especially for our Zoom members, as groups work, they should share progress on Slack. That's a nice thing.
Exactly. Okay, so I'm just about to push this to the hub and it will include the link with the drive for the data.